Hi, and welcome to this section of the Probability and Statistics Tutor. And in this section, we're going to build on what we did in the last section dealing with probability distribution functions when we introduced that. And we're going to, in this section, talk about our first real probability distribution called the binomial distribution, okay? So the binomial distribution, when you read it for the first time, it really sometimes can make you feel confused and make you feel like it's a really tough thing, but the thing that you need to know is that it's really not a big deal, okay? What we learned in the last section is that a probability distribution function is just a really fancy big word, and all it really means is that you have functions from Algebra 1. You put a number in, you get a number out. Well, these probability distributions are functions, so to speak, that instead of just getting any old number out at any given value of your random variable x, you have a probability of that variable actually occurring with that value. That's what's happening here. So this is a binomial distribution. It's a specific type of distribution, okay? In the last section, we were talking in general terms. Here's a probability distribution, and I just write it down in a chart form or in a histogram form, in a bar graph or something to kind of show you what it is, and we learned about them. In this section, we're going to study a very specific, very useful, very common probability distribution called the binomial distribution. So what we're going to find for each of these problems, really, is that once you learn the way the problem is constructed and know that it's a binomial distribution, what's going to happen every time is you're going to write down with your pencil, you're going to write down an actual function. F of x is equal to, and you're going to write down what this function is, just like a function from Algebra 1. Or trigonometry or something. F of x is equal to x squared. At one time that looked really foreign to you. So here in the beginning with the binomial distribution, it's going to look a little foreign to you. But once we tackle some problems and see how it's applied, it's not a big deal. It's actually not a big function at all. So what we're going to do is we're going to write down this binomial distribution. We're going to learn how to calculate the values of the function at various values of x, and we're also going to talk a little bit at the end about using the tables in the back of your book that almost every book on statistics will have, and teach you kind of how to use those as well. So most books will just start out by writing down what the binomial distribution is and telling you to learn it and love it and try to teach you how to do it. I want to start out with an example because I feel that that's the best thing to do. So forget that we're learning about something complicated called a binomial distribution and just work with me on this example, okay? Here's what I want you to think about. Let's say we have 4 questions on a test. It's a multiple choice test. So there's question 1, question 2, question 3, question 4. I have no idea what this test is about, okay, because I didn't study. So I'm going to guess at this test. Each question has 5 choices, A, B, C, D, and E, right? So it's actually something you might actually enjoy learning about anyway, just for giggles, because what I'm going to end up asking you is what's the probability of getting some of these questions right and wrong, okay? And what's the probability of doing well and doing poorly on the test, okay? So 4 questions, and each question has 5 choices, okay? So let me ask you this. If you completely guess at any given question, no, forget the fact that there's 4 questions. On question number 1, if I completely guess at it and there's 5 choices, what is the probability that I'm going to get that question right? 5 choices. All right, so learning from probability, we know that there's only one way to get the right answer, and there's 5 choices. So the probability of getting the right answer is 1/5, right? Okay? Okay, so the probability of guessing on one of these questions, just the first one, okay? The probability of getting the right answer, I'm going to call that probability P, okay? Just P, so that's what I'm going to call it, and I'm going to say that it's equal to 1/5 because we just said that the probability is 1/5 since there's 5 choices, and we're going to go and convert that to a decimal. I think you can convince yourself, if you put that in the calculator, you'll find out that the probability is 0.2, okay? 1/5. Now, what would be the probability of the wrong answer, of guessing the wrong answer? The probability of the wrong answer. So again, it's just question number 1. It's 1/5 that we got the right answer. How many choices, how many wrong choices are there? There's 4 wrong choices in every single question, right? So the probability of getting the wrong answer is pretty high, 4/5, because there's 4 ways to get the wrong answer and only 5 choices. So instead of using P, I've already used that thing, so I'm going to call him Q. And we already said that the probability of Q getting the wrong answer is 4/5, but we also know that Q is equal to 1 minus P. And we know that's equal to 4/5 because we just said it's equal to 4/5. In other words, if the probability of the right answer is 1/5, then the probability of the wrong answer is just 1 minus the probability of the right answer. And we've been doing this 1 minus business ever since the beginning of the probability, so that should not look foreign to you. Okay, if it is, go back and review that now. So probability of right, probability of wrong, and so you would guess this is 0.8. 1 minus 0.2 is 0.8, right? So far, it hasn't been rocket science. So for one question, the first one on the test, 1/5 of being right, 4/5 of being wrong. Okay, now the question I'm going to ask you, and actually the form of all of these binomial distribution things that we're going to learn about, the form of the question is always going to be like this. What is the total probability for this particular problem of guessing 3 out of 4 of the right answers? Of the questions correctly. So 4 questions, 1, 2, 3, 4. We know what the probability of getting the questions right and wrong is of each individual question, but now that there's 4 questions, we just want to calculate what's the total probability that I get all 4 of them. In this case, out of 4 of them, I get 3 of them right. Only 3 of them right. I don't want to get 2 of them right. I don't want to get 4 of them right. I want to know what the probability of only getting 3 out of the 4 questions right. Okay. So how do I do that? Well, let me just, before we even calculate it here, let me just write a few things down, okay? If I have question 1, question 2, question 3, and question 4 right here, just work with me here, okay? Well, first of all, I could get the first one right. I could get the second one right. I could get the third one right. And I could get the fourth one wrong. Right? Because the whole thing is I want to get 3 questions right and 1 of them wrong. That's what I'm trying to do. What I'm going to end up defining here as a success in this little experiment is 3 questions right, 1 question wrong. In fact, I'm going to go ahead and write that down right now. So I'm going to call, for this particular example, success is 3 questions right and 1 question wrong. I have to get that because that's what the question asked me. I want to know what the probability of getting 3 of them right is. Only 3 of them right. So I could get the first one right, the second one right, the third one right, and the fourth one wrong. But I think you'd also agree that I could get the first one wrong. And then I could get right, right, and right. All right, so I could have the first one wrong and then the next 3 right, or I could have something crazy like, you know, right, right, wrong. I promise there's a point to this. Right. So I could have right, right, wrong, right. Okay. The point is what I'm trying to get at here is the problem is a little bit more complicated than when you might first think, when you first look at it. Because I know that when I first looked at these things a long time ago, I'm thinking to myself, well, the probability of getting a single correct answer is 1/5, and I know I only want 3 questions correct, so I'm just going to multiply it, you know, 1/5 times 1/5 times 1/5, and I'm going to be done. Well, that's not exactly right, you see, because inside of this particular sequence of events, that would be right. 1/5 probability of getting right times 1/5 times 1/5 times 4/5, because that's the probability of getting wrong. And that would be the right answer for this particular sequence of events. But I've just shown you that that's not the only sequence of events that could give you the success, quote unquote, of getting 3 right answers. This one could be wrong, and this one right, right, and right. And this one could be right, right, wrong, and right. And I could go down and populate the table, you know, to all the way to the end and show you that there is a number of different sequences of getting right and wrong answers to satisfy what I'm trying to find out, which is what's the probability of getting only 3 questions correct, okay? So because there are different ways, different combinations, which is where we're going with this, different combinations of getting right and wrong answers to satisfy what I'm trying to do, the calculation of the probability isn't maybe quite so easy as you'd think about initially, okay? But it's not that hard to understand. I mean, let's just keep working with this, okay? We know the probability of the right answers, and we know the probability of the wrong answers. And we know that within each sequence of events, like I could take the test on Monday and do this way, and I could take the test on Wednesday and do it this way, and on Friday and do it this way. All of them satisfy what I'm trying to find out, the total probability of getting 3 questions right. So I know, by looking at just one of these lines, I know that the probability is going to have something to do with the probability of the right answers and the probability of the wrong answers, right? So I know, for instance, that since the probability of the right answer is 0.2, and since I have 3 of them in each sequence, in each success, you'd say, right answer, right answer, right answer, I know that I'm going to have 0.2 times 0.2 times 0.2, because this is basically, since it's question 1, 2, 3, and 4, this is sort of like event 1, event 2, event 3, and event 4. So I know I'm going to have 0.2 times 0.2 times 0.2. That just comes from the very first section in the class, you know, in the beginning of it when we're talking about, you know, sort of the fundamental counting principle. I know that the total probability here is going to have something to do with the probability of each individual right answer, okay? Because if you remember back to the multiplication principle of probability. The probability of multiple events ANDed together is basically going to be the probability of each one multiplied together. Okay, we learned that just not too long ago. So right answer, right answer, right answer, they have to be multiplied together because I'm saying and, okay? And I know I have a wrong answer in here, so I know I'm going to have a probability of 0.8 that's going to come into play here, and I'm going to go ahead and put an exponent of 1 just to show you he's only multiplied one time. So for this sequence of events, let's say I take the test on Monday and do it this way, I'm going to have 0.2 times 0.2 times 0.2 times 0.8, okay? If I come in on the next day, it's a different sequence of getting right and wrongs, but it's really the same numbers multiplied together. This wrong is the 0.8, right, right, and right are these three 0.2s, okay? And then so on and so on. So every time I come in on a different day of the week and take the test, if I get a different questions right and wrong, but in the end if I always get 3 right, I'm going to end up calculating the same thing each time I do it, but the total probability, the total number of ways that I can actually satisfy what I'm trying to do, which is find out what's the total probability of getting 3 questions right, the total number of ways to do that is going to be this probability that I've calculated multiplied by something. It's got to be multiplied by something to kind of take into account the fact that on different days of the week I could come in and get different questions right and different questions wrong. So let me ask you this, what should I multiply by? What should I multiply these probabilities by to take into account the fact that this one that I wrote first is not the only sequence of questions right and wrong that I could actually end up doing? Well, let me ask you this. I have 4 questions, okay? I have 4 questions, but I only have 3 right answers. So the number of combinations that can happen is going to exactly be what we studied in the very first section of this course, the number of combinations. 4 questions taken 3 at a time to get the right answer is going to be the total number of combinations in which this stuff can happen. So when you see this is just the probabilities multiplied because I have right answer, right answer, right answer, and I was given in the problem basically what this probability is. The wrong answer is because every time I do this, I'm hoping for 1 wrong answer. That's what I'm trying to do. And then this out front is the total number of combinations in which all this stuff can happen. So when you multiply all this out, that is going to give you the total probability. That is going to give you the total probability. So expanding on this more, this, you should remember, is 4 factorial over 4 minus 3 factorial times 3 factorial. Okay, and then when you multiply this, 0.2 times 0.2 times 0.2, you get 0.008, and then of course the 0.8 stays the same. Okay, and then on the top here, you're going to have 4 factorial. 4 minus 3 is 1 factorial. Okay, 1 factorial is just 1. So what you're going to have is 4 times 3 times 2 times 1 over, and on the bottom, since this is 1 factorial, he disappears. Over here, you're going to have 3 times 2 times 1. Okay, and then you're going to be multiplying by 0.008 and 0.8. Okay, and so at the end of the day, what's going to end up happening here is for these factorials, all this stuff's going to cancel. So you're going to have 4 times this, and when you actually do all of that, the actual total answer is 0.0256. Okay, that is the total probability of doing that. Now, it's very, very important that we understand what we did in this problem, because in a minute, I'm going to write down the binomial probability distribution, and it's really going to follow exactly from what we did here. So if you understand this, you'll have no problem understanding the general form of the distribution. So we were told we have 4 questions on a test, each with 5 answers. So we know the probability of getting a single question correct is 1/5. We're always going to call that P. In all of these binomial distribution problems, the probability of a success within the kind of the string of things you're doing is always going to be called P. So remember that. The success is always going to be called P. The probability of failure, I'm calling getting the wrong answer a failure, which is the opposite of the success, is always going to be 1 minus P. And so that's going to be, you know, whatever's given in the problem as well. And you can always calculate Q once you know P. It's just going to be 1 minus P, okay? Now in this problem, given that stuff, and we had the 4 questions, we want to know the probability of getting only 3 and only 3 questions correct, and 1 question wrong. So I was trying to show you by example here that even though you can get 3 questions right and 1 question wrong, there's different ways to make that combination happen. Okay? And each way that it can happen is a valid outcome, and because of that, the total probability needs to take into that into account. So since each probability of right was 0.2, and I have 3 of them, because that's what the question said, 0.2 times 0.2 times 0.2 times my failure, to round it out, 0.8, and then times this thing in front, the combination of 4, taking 3 at a time, because I had 4 questions, take 3 right ones. That's the total number of ways you can arrange that stuff, and you do the math and you get it. So that basically is the binomial distribution. I just haven't really told you that, and I haven't generalized it into what you would actually see into your book. So before we do that, which is going to be very, very soon, I'm going to write down a few things to give you some helpful hints to know when the type of problem that you're working is actually a binomial distribution. So let me write a few things down. A binomial distribution, a binomial probability distribution, has to have the following things true. If every one of these things is true, then it is a binomial probability distribution. The first thing is it has to have a fixed number of trials. Okay? Every time I come and give you a new constraint, I'm going to show you back to our example why it's true. Fixed number of trials. All this means is we had 4 trials here. Okay? We had a fixed number, 4 trials. The question was how many questions we get right out of 3 wrong answers. So the number of trials is sort of like the number of things you're doing. Some of them are going to be quote-unquote successes, and some of them are going to be quote-unquote failures, okay? But it's always 4. That's where it doesn't change, and that's always going to be true for this type of problem, okay? The second thing is that the trials have to be independent. What that means is, remember, conditional probability. If one event influences the next event. If I'm taking a test, if I answer a first question right, whatever I answer for the second question should have nothing to do, if it's a random guessing, is going to have nothing to do with the first question. So these are independent events. I go question 1, question 2, question 3, question 4, making my guesses. And as long as they're independent, that's what that second thing's trying to say. Okay? Each trial outcome must go into 2 categories. And we're calling these success and failure. Again, relating it back, it's really easy to understand. In this question, if I answer question number 1, I'm either going to get the right answer or the wrong answer. It's 2 ways to come out, right or wrong. That's it. Okay, there's no in-between state. There's no maybe. There's no ambiguity or anything. It's either right or wrong. It's flipping a coin would be another good example. Heads or tails. There's no third choice, okay? So that's why it satisfies this is a binomial distribution. And then the final thing that you usually see is that the probabilities must remain constant for each trial. Okay, and that's exactly what happened here. We know when we're guessing on a test that the probability of success of getting a right answer, let's say, is 0.2. And that's going to be the same probability as I go question to question. If I go Monday, Wednesday, Friday, if I go question to question, the probabilities here are going to be the same. They're never going to change. So that's exactly what you're going to see in your book as sort of like things to look for binomial distribution. You have to have a certain number of trials. In this case, we had 4. You have to have them independent. You have to have the probabilities remain constant, and you have to have either 2 outcomes, right or wrong. Okay, so once you get the hang of looking at it, it's not going to be that big to identify when it's binomial or not. Let me go ahead and write a couple more quick things down, and then I'm just going to throw up the actual binomial probability distribution up on the board for you. Okay, we've already talked about this, but I'm going to write it down explicitly for you. P is what we were calling just a minute ago the probability of getting the right answer. This is the probability of success in one trial. Okay? And I'll relate this back to you in a second. 1 minus p, also known as q, which is exactly what we just talked about again. This is the probability of failure in one trial. Back to our example. This is the p is the probability of getting the right answer, and q is basically the complement of that, the probability of failing, of not getting the right answer. Okay. This is something a little bit new, but not a big deal. N is called the number of trials. Okay, and x is the number of successes in trials. Okay? Now, it's very, very, very important that you understand this stuff as it relates to our example, because you see, the reason why I started out with an example to begin with is because I really want you to internalize it. Okay? I want you to understand this example so well that when you read a new problem in your book, you'll immediately think back to this example about questions on a test to figure out how to relate the example in the book to that. Because once you understand this, all the problems are going to look like it, and you'll be able to come back as sort of like this nice, secure, comfortable memory of something that you really understand. So when you see a problem you don't understand, you'll be able to pick the numbers out of the problem and relate them to this. So let's do that, okay? P is the probability of success in one trial, okay? Q is the probability of failure. So this is getting the question right, this is getting the question wrong. N is something new I haven't told you about. It's the number of trials. Going back to our particular example, okay, there's 4 trials, 1, 2, 3, 4. Okay, think of them as sort of like events, okay? 1, 2, 3, and 4, okay? Within each event, so to speak, I have a probability of getting it right and a probability of getting it wrong. I know the probability of getting it right is 0.2. The probability of getting it wrong is 1 minus that, 0.8. It's always going to follow this pattern. There'll be a probability of getting right and a probability of getting wrong, okay? So this is the number of trials, N. The last thing that you have to know to be able to apply the binomial distribution, X is the number of successes in N trials, okay? It looks foreign and crazy and cryptic on the board, but you already know what it is here. X, in this case, is 3, okay? 3 was the number of right answers in 4 trials. So it's imperative that you understand this, okay? There were 4 trials because there were 4 questions, and I wanted to know what was the probability of getting 3 of them right, so X was equal to 3. Okay, X was equal to 3. What we're going to actually calculate in just a minute when I write it on board is a general function, because it's a distribution function. You're going to end up getting f of x, okay? X, I'm telling you, is the number of successes. So what you actually write down usually, the probability distribution function, is going to be a general function f of x that you can then plug in different values for x, whatever you want, and you'll get probabilities out. Just like in the last section, we made a table of x and a probability. Here we're going to write down an actual function, just like from algebra, where you plug in an x. In this case, x is the number of right answers that I want, and I'm going to get back a total probability out. So the problem could have been rewritten to be, what is the probability of 2 questions right and 2 questions wrong? So N would still be 4 because there's 4 trials, but in that case you would have x is equal to 2 because 2 would be the number of successes in N trials. If I wanted 1 question right and 3 questions wrong, I would have x is equal to 1. And so when I write down my distribution function f of x, I would write that down, and then I could put 1 success, 2 success, 3 successes, or all 4 successes. I could put them in as x, and I would calculate the probability. So the distribution function you're getting is going to let you solve the problem for any number of correct questions, or whatever the analog is in the problem that you're looking for. But in this problem, it would be however many questions that you wanted to calculate correct out of 4 questions. 4 is the number of trials. So without talking about it anymore, let me go ahead and just write it down, what the binomial probability distribution is. I told you it was going to be an actual function, f of x, where x is the number of successes in N trials. Okay, it's going to look very similar to what you already expect. It's going to be the combination of N taken x at a time, okay, times the probability of success raised to the x power times the probability of failure to the n minus x. Okay? And because this is just a combination, this is just the combination that we learned from the very first section of the book. Some books will just expand that out for you. This is going to be n factorial over n minus x factorial times n factorial times p to the x times q to the n minus x. They're exactly the same thing. It's just this is just a compact way of writing this. Okay? So basically what's happening here, this is literally called the binomial distribution function, probability distribution function. Now remember what a probability distribution function is. In the last section when we were showing them, I wasn't really showing you too many functions like this. I was writing tables. I was writing a table of x and f of x, right? And for every value, for your random variable that comes in, I was showing you the probability, and we were talking about all kinds of things related to that, just to kind of get the point across. Here, this is a very specific probability distribution. It's called binomial because of the way it's named and the fact that it's got this binomial coefficient in it. If you remember, this is a combination thing from section 1, but it's also called a binomial coefficient. And that's why it's called a binomial probability distribution. But this is no different than what we've just done with numbers. So don't freak out when you see this. First of all, remember that we had the probability of success. This is the probability of getting a right answer. And we had this right here in our problem here. 0.2 was the p. That was the probability of success. We had a cube here because we knew that we wanted to calculate the probability of getting 3 of them right. So it's 0.2 times 0.2 times 0.2. So that's why it's p to the x power, because x is the number of successes. That will be, in this case, the number of right questions out of 4 total questions, okay? N is, in our example, 4 because there were 4 questions. So if you have 3 questions here and n minus 3 questions here, basically whatever you have here and whatever you have here have got to add up to equal n, okay? So if you have, in our example, we had p cubed, and then we have q to the 1 power, because n was 4, so 4 minus 3, x was 3 for 3 correct questions, 4 minus 3 gives me 1. So going back over here, I had p cubed times q to the 1st power. These two things are always going to add up to the number of questions you have, basically is what it is. Whatever you have here, this one's going to have to be the exponent to make it add up to the number of correct answers. I mean, to the total number of questions you have, if you're using this as sort of your example, because you have 3 correct, you must have 1 incorrect. So these things have to add up to the total number of questions. So this is sort of a math way of writing that down, okay? You have x correct questions, the number of successes, and n total questions. So n minus x is going to be the number of wrong answers. So, and q is the probability for the probability of getting a wrong answer. So it's q raised to that. And then finally, what's in front of it is just the number of combinations of n questions, n trials, n questions taken x at a time. X is the number of correct answers. So that will be over here, 4 and 3. 4 questions taken 3 at a time. That's exactly what you have here, and then the rest of it is just expanding this out. So play this again if you need to, because what's going to happen is we're going to go and do some problems here. We're going to jump right on into it, and we're going to throw this up every time. And the first thing you're going to have to do is you're going to have to throw this up on your piece of paper, and you're going to have to figure out, okay, in this problem, what is n? That's the number of trials. What is x? That's how many successes I'm looking for. What is the probability of getting a success? And what is the probability of getting a failure? And then you're going to crank through this. So really the only thing you're trying to do is identify that it's binomial and then identify the right information so you can just go ahead and calculate it. And that's what we're going to do here. So go ahead and watch this a little bit if you need to, and then proceed with the remaining problems in the section, and you'll be in real good shape for this type of distribution function. Okay, now the first question, again, these all follow the exact same mold of what we have just done. So let's read it, let's identify the information in it, make sure it's binomial, and then apply what we've just done. 9% of men are colorblind, okay? If 6 men are chosen at random, find the probability of exactly 2 of them being colorblind, okay? That's what the question says. Read it again, make sure that it follows the mold of what we're trying to say is a binomial distribution. 9% of the men are colorblind. If 6 men are chosen at random, find the probability that exactly 2 of them are colorblind. So without writing anything down, when you think about what you're doing, you're pulling 6 people from the population. So that's sort of like an event, right? So basically it's a trial, okay? So there's 6 trials. N is equal to 6. Well, I haven't even written anything down yet, I'm just telling you this. N is equal to 6 because we pulled 6 people. Of those 6 people, we want to know what the probability of only 2 of them, 2 and only 2 of them, actually being colorblind. So x, which is the success, the number of successes in trials, x is going to be 2. So x is going to be 2, and n is going to be 6. Now we know what the probability of person being colorblind is. So that's sort of like our probability of success, the number of people being colorblind. We know what that is. So we have everything we need to write down this binomial distribution. We know what n is. We know what x is. That's the number of successes. The probability of success, I put it in quotes because being colorblind is not really a success, but in this problem it's what we're talking about, so it's a success. We know the probability of that, and we know what the probability of not being colorblind is because you can always calculate that. When you know what P is, you can always find Q. That's all you need. The rest of it just follows from that. So basically, if you want to sort of draw a picture, again, to kind of reinforce what we're doing, you're pulling 6 people from the population, right? So you're pulling 6 people. So this is person 1, person 2, person 3, person 4, and person 5, and person 6. So just for instance, this person could be colorblind, this person could be colorblind, this one could be okay, which means not colorblind, okay, and okay, and okay. We're trying to find the probability of exactly 2 people being colorblind, of 6, okay? And of course, somebody else could go down the street and pull 6 different people in a different order, you know, or the same people even. The same 6 people, I could choose them in a different order, right? And the first one I could choose would be okay, and this one could be colorblind, and then this one could be okay, and this one could be okay, and this one could be colorblind, and this one could be okay. This one would still be a quote-unquote success because I still have 2 colorblind people in the group of 6. So I'm just reminding you here that yes, there's 2 people colorblind out of 6, but there's multiple different ways to arrange those 6 people to get what you're looking for. Okay, so we're going to have the probability of being colorblind involved, and we're going to have the number of combinations of how you can arrange these colorblind people as part of it, okay? So what we've said is that the probability of being colorblind is 9%, 0.09. So that guy would be 0.09. This would be 0.09, right? And then, of course, if these guys, the probability P is 0.09, then the probability of not being colorblind is 0.91. 1 minus P. So here's an okay guy, here's 0.91, 0.91, 0.91. All I'm really doing is drawing it for you graphically to show you that pretty high odds he's okay, low odds, high, high, low, high. Okay, I'm just laying it out. Here you'd put the numbers in the different places depending on where you were at. So let's go ahead and just write this down with certainty. We know from the problem that the probability of actually being colorblind is 0.09. And so we also know that the probability Q, which is exactly equal to 1 minus P, is 1 minus 0.09. We already talked about it, 0.91. So here we found 2 of the parameters that we need for our binomial to use the binomial probability distribution. Okay, we found 2 of them, so what else do we have to know? How many people are there in a trial? Well, there's 6 people we're picking, right? So the number of trials is 6. Of those 6 people, how many are we trying to calculate are colorblind? Well, that would be X, and that's 2 people. So I believe with this, this information, we have enough information to go ahead and use the probability distribution. So N is equal to 6, which is the number of men picked. And X is equal to 2, the number of men colorblind of those picked. Okay? All right. So without further ado, let's just go ahead and write down what the probability distribution is. Okay? From the previous board, I'm going to first write it down exactly how it is. So f of x is going to be equal to, this is how we wrote it down, n combination with x, p to the x power, q to the n minus x power. Okay? N minus x power. Pretty simple formula, but you know, this gets a little bit more expanded when you write it down. So if we're going to use what we have here, all you do is you put in what you have. This is going to be, if I wanted to write down the general form of it, okay, it would be n is equal to 6, combination with x, which we know is equal to 2, p to the x, q to the 6 minus x. Okay, all I've done is I've plugged in what n is. That's all I've done. I haven't done anything else. I'm just kind of showing you where it would go. Okay, so if you wanted to calculate, let me just do one more thing here. Okay, let me just do one more thing here. So if I want to just leave it in terms of x, p, we know probability of being colorblind is 0.09 raised to the x power. Q we also know, is 0.91 raised to the 6 minus x power. This is actually what you would write down as the binomial probability distribution of this function. It's not the answer because we haven't calculated any probability yet, but this is the binomial probability distribution. It's a function, f of x. You plug in x here, and here, this is going to evaluate to a number. This is going to evaluate to a number. This is a combination. It can evaluate to a number. And what you're going to get is a probability. So in this particular problem, I'm trying to find out what's the probability of getting 2 colorblind people out of 6. So I could plug x is equal to 2 in here, and I'm going to get that answer. If the problem were different, what's the probability of getting 4 colorblind people out of 6? All I would do is use the same function and put a 4 in here. I get a different number here, a different number here, and a different number here. Okay? So I would get a different probability back. And so what I'm trying to tell you, it truly is a function just like any other function you know. You put in what x is, which is the number of successes of men being colorblind, and everything's going to change accordingly. Everything here is going to change accordingly to give you the right probability. So let's go ahead and plug in f of 2, which is the probability of 2 people being colorblind, and that's going to be combination of 6 with 2, 0.09 raised to the 2 power, 0.91 raised to the 4 power. Now do you see what's happening here? 0.09 squared. That means I have 2 colorblind people that I've picked, 0.09 times 0.09. Those are the 2 probabilities of success. The other remaining 4 people, that's why I have a 4 here, is the 0.91 times 0.91 times 0.91 times 0.91. They make up all of the people that in this 6 that I've chosen that are not colorblind. And then finally in the front I have a multiplier here, which is the combination of 6 chosen 2 at a time. Those are all the different ways that I can arrange picking these people. You know, maybe the first 2 people I pick were colorblind, and then if the next week I go get some other people, maybe the last 2 people I pick were colorblind. All of those different scenarios are going to relate to the total number of ways I can choose those people. Okay, so let's go ahead and calculate it. What I'm going to have here is 6 factorial over 6 minus 2 factorial times 2 factorial. And then the 0.09 squared is going to be 0.0081, and then the 0.91 raised to the 4th power, 0.686. Okay? And then what you're going to get here is 6 factorial over 4 factorial over 4 factorial times 2 factorial. Just the 6 minus 2 is really all I've done. And you're going to have the same stuff over here, 0.081, and you're going to have the same stuff over here, 686. Okay? And so at the end of the day, what you're going to have is, because you have 6 factorial and 4 factorial, is 6 times 5 times 4 times 3 times 2 times 1 on the top, and then here you have 4 factorial times 3 times 2 times 1. So what you're going to actually have is just 6 times 5 on the top times 2 times 1. Everything below 5 times 4 times 3 times 2 times 1 cancels with the 4 factorial. Again, times the same number, 0.0081 times 0.686. Okay, and then finally 6 times 5 divided by the 2, and then you multiply by everything over here. What you're actually going to get at the end of the day is 0.083. So the f of 2, the binomial distribution of this problem evaluated at 2 successes is 0.083, okay? So going back up to the top, we identified what the probability of a person being colorblind is. We know what the probability of a person not being colorblind is. We know that we're trying to pick 6 people, and we know that we only want to find the probability of 2 of them being colorblind. So this is the general form for the binomial distribution. Okay, n is equal to 6. And so if you put n is equal to 6 and put your probabilities in, this is the actual function. I could put x is equal to 1 colorblind person, 2 colorblind people, 3 colorblind people, and 4 colorblind, all the way up to 5 and 6. I can go all the way from 1 to 6, and for each number I'm going to calculate a different probability, okay? And that's why it's a function. So here we're evaluating only at 2 people, and then the rest of it's just math, evaluating it all down and getting 0.083. Now the next problem again is very similar, and it goes like this. The IRS audits 1% of tax returns. If you look at the whole population of America, 1% of people get audited, okay? If a tax prep service, tax prep company, submits 5 tax returns to the IRS, what is the probability that exactly 3 people are audited, okay? Exactly 3 people are audited. So the IRS does 1% auditing, and when we submit 5 returns, what's the probability of 3 of them actually getting audited? So again, it follows the same mold. We know what the probability of success is, that's the 1%, Okay? We know that we submit 5 returns, so that's n is equal to 5, and we know that of the 5, 3 of them get audited. That's what we're trying to calculate, so x is equal to 3. So we really have all the information we need to go ahead and just jump right in, okay? So before we actually get started, just to kind of draw a little picture, we know that we submit 5 tax returns. I like drawing pictures, that's why I do this all the time. And we know that we want to find the odds or the probability of 3 of them being audited. So this guy could be audited, this person could be audited, this person could be audited, this one could be not audited, and this one could be not audited, because I'm trying to find the probability of only 3 people getting audited. But if I submit different 5 tax returns, then it could be totally different. This guy could not be, this guy could not be, and then these 3 people could be audited. So it's going to involve, just like all these problems, the probability of being audited, the probability of not being audited, and then a multiplier in front that tells you the number of different ways all this stuff can be arranged. That's going to be the total probability. So from the problem, the probability of success, and I'm calling being audited a success, if you can believe that, 0.01, 1%. Just move the decimal point 2 places to the left, okay? Q is always going to be 1 minus P, so it's 1 minus 0.01, so it's 0.99. That's going to be the probability of not being audited, okay? N, which is what we always need, is the number of trials, which is 5. So I'm going to put it right here, the number of trials, to help you remember what that is. And X, for this particular problem, X is going to be the number of successes within those 5 trials. So it's 3, and that's the number of audits of our 5 submissions. So that's it. That's all the information we need to actually use the binomial distribution. So again, the binomial distribution in general is a function in combination with x times p to the x times q to the n minus x. Probability of success, probability of failure, this is all within the trials, times a multiplier to arrange them all in all the different ways that it can happen to get the total probability. Okay? And again, if you wanted to expand this, this is n factorial over n minus x factorial times x factorial times p to the x times q to the n minus x. I've just expanded the combination there for you. Okay? So if I wanted to calculate this binomial distribution at the value x is equal to 3, because I have 3 quote-unquote successes, 3 audits that I'm trying to calculate the probability of getting, then n is going to be equal to 3. So it's going to be 3 factorial. I'm sorry, x is going to be equal to 3. Okay, x is going to be equal to 3. So what I'm going to have on the top, since I have 5 trials and n is going to be equal to 5, it's going to be 5 factorial over 5 minus 3 factorial times 3 factorial, because x is 3, times p. The probability of getting an audit is 0.01 to the power of 3, because I have 3 audits I'm calculating the probability for, times q, which is 0.99, okay, to the power of 2. These two things have to add up to the total number of people I'm submitting. That's why it's x and n minus x. That's what that does for you. Okay? So all I need to do is calculate all this stuff, and I've found my answer. Okay, so let me switch colors here for a second. What I'm going to have on top here is 5 times 4 times 3 times 2 times 1. On the bottom, 5 minus 3 is 2 factorial. Okay, so I'm going to have 2 times 1 times this, which is 3 times 2 times 1. And the 0.01 cubed is going to be 0.000001, and then the 0.99 cubed is 0.9801. Okay? I'm sorry, the 0.99 squared is 0.9801. All right, now you can see here the reason I expanded this is because these all cancel, so it makes everything easy. So 5 times 4 divided by 2 multiplied by all this stuff is going to give you the probability of 3 people getting an audit of 0.000098. Okay, so it follows the same mold. Probability of getting 3 successes out of n trials. I just have to know the probabilities involved, and then I've got it. Now I could use this function to calculate the probability of getting 4 audits out of 5, or 5 audits out of 5, or 1 audit out of 5. It's truly a function. I can use it that way. The probabilities are going to stay the same. You just plug x and n in appropriately, and you'll get the right answer. Okay. Now let me ask you a follow-up question. This is the probability of getting 3 people audited, 3 and only 3 people audited. Now what if I asked you the question, the follow-up question, what is the probability of at least 3 people getting audited? What's the probability of at least 3 people getting audited? Now when you see the word at least, it means I have 5 people I've submitted. At least 3 people means 3 people could get audited, 4 people could get audited, or 5 people could get audited. I can't get 6 people audited because I only submitted 5 people to the IRS to begin with, okay? So if you have a problem like what is the probability of at least getting 3 people audited, then you need to start doing some addition, right? The probability there of at least 3 people is going to be 3 people getting audited, the probability of that, plus the probability of 4 people getting audited, plus the probability of 5 people getting audited, okay? That's what you need to add together. We've already calculated the first one. We just need to calculate the probability of 4 and 5 people, and then we've got it. So the probability of 4 people getting audited, just following the formula here, going back up here, basically over to here, if n is still going to be 5, so it's 5 factorial, but now it's 4 people that I'm trying to see are getting audited, so it's going to be 5 minus 4 factorial times 4 factorial, okay? And again, I'm still going to have 0.01, but now it's going to be raised to the 4th power, and 0.99, now it's going to be raised to the 1 power. These are my 4 people that are getting audited, low probability of getting audited. This is my 1 person not getting audited. Okay? Now when you crank through all that, raise this to the 4th power, and do the factorials and all this stuff, what you're going to actually get for this probability is a very small number, 0, 0, 0, 0, 0, 0, 0.495. Okay? 0.495. And then equivalently, the probability of getting 5 people is going to be 5 factorial over 5 minus 5 factorial times 5 factorial. All I've done is plug a different value in for x. And then here I'm going to have my 0.01 to the 5th power. And then I'm going to have my 0.99 to the 0 power. And these are my 5 people that get audited. That's why there's 5 there. And this is my 0 people that do not get audited. And so when you crank through all of that, you're going to get an even smaller number. You're going to get 0.000 000 1. Very, very small number, okay? So we know what the probability of 3 is, we know what the probability of 4 is, we know what the probability of 5 is, so the total probability of at least 3 people getting audited is adding up all 3 of those, probability of 3, 4, and 5, and what you're going to get is 0.000000985. 0.0000985. Okay, so when you see something like at least, you basically are going to end up having to add different things up, or a minimum of, or something like that, or even if something said what would be the probability of getting a maximum of this many people, then you're going to have to just think about what that means and calculate the individual probabilities given by the binomial distribution for each one of those and add them up. It's really the same thing that we were doing before in our probability theory. It's just that now we've actually got a function to help us calculate the probabilities for each case, and so then you calculate them and add them as you need to answer whatever the problem is asking you. Okay, now the next problem again is going to be similar, and it says a company hires employees who they're not gender biased. The people making the hiring decisions are not gender biased, so they hire men and women with equal probabilities. Okay, that's what that means. If a company hires 20 people, find the probability that they hire 2 or fewer women. Okay. So you would expect that if they hire without gender bias, and if everyone's equally qualified, they should hire roughly 50-50 men and women, right? But this is saying that of 20 people hired, find the probability that they only hire 2 or fewer women. That's what we want to find. So we know, basically we know that n is equal to 20 because they've hired 20 people. So that's the number of trials, okay? The probability of a success is that they hire women, and we, from a probability point of view, should be 0.5, okay, because it should be without gender bias. That's what it means. Probability of hiring men and women should be the same, okay? The probability of Q, which is 1 minus P, should also be 0.5. This would be the probability that they've hired a man, okay? So 50-50 chance is what we're doing here. This means there's no bias, okay? Now, the actual binomial distribution function, just to remind you, is n combination with x, p to the x, q to the n minus x. We know what p and q are. We just found that. We know that n is 20, and so the question is actually asking us, what is the probability that they hire 2 or fewer women? But before I go there, let me go ahead and plug in what n is and p and q. N is 20, x is a variable, I'm going to leave it there. P is 0.5 to the x. Q is 0.5 to the n minus x. And actually, since we know n is 20, this is going to be 20 minus x. So here we actually have a function of x. We put x in, and what we're going to get out is that probability. I wanted to write that for you. Because the actual probability that we're looking for is the probability that they hire 2 or fewer women. So the probability there is going to actually be equal to the probability that they hire 0 women plus the probability that they hire 1 woman plus the probability that they hire 2 women. No more than 2 because it says 2 or fewer women. So there's a chance they could hire 0, 1, or 2, and we have to add them up. This is just like the last problem, okay? So let's go ahead and start calculating probabilities. The probability that they hire 0 women is going to be 20 in combination with 0 times 0.5, x is 0, times 0.5, 20 minus x is just going to be 20, okay? And you know that this combination here is just going to be 20 factorial times 20 minus 0 factorial times 0 factorial times 0.5 to the 0. Anything raised to the 0 is 1, and then the 0.5 raised to the power of 20, okay? So what you're going to have when you take 20 factorial and divide by 20 factorial, this is just going to give you 1 in here, and 0 factorial is always going to be 1. So you have 1 times the 0.5 to the power of 20, and so what you're going to actually get, the probability of hiring 0 women is pretty small, 9.53 times 10 to the minus 7. So there's a lot of zeros in front of here, okay? Because the fact that, this is basically equal to, if you don't really understand scientific notation, is 0.0000009, 1, 2, 3, 4, 5, 6, 7, 5, 3. You just have 953 and you have 1, 2, 3, 4, 5, 6, 7 places you scoot the decimal in front. That's all that means, okay? So it's a very low probability, and that makes sense because if they were hiring people with equal chance from men and women, it should be very, very low that they actually hire 0 women. Okay? Now let me switch colors for a second, and let's find the probability that they actually only hire 1 woman. It's going to be 20 factorial because n is a constant 20, and on the bottom it's going to be 20 minus 1 factorial times 1 factorial. And then over here we have the 0.5 to the power of 1, and then we have 0.5 to the power of 19. This is my 1 person I hired as a woman, and this is my 19 people that I did not hire as women, and then here is just the number of combinations, okay? And when you do all this factorial and you multiply by all this stuff here, what you're going to get is the probability of hiring 1, and only 1, is 1.907 times 10 to the negative 5, which again, if you're not comfortable with scientific notation, is 0.0001907. 1, 2, 3, 4, 5. There's 5 decimal places I moved in front of there, okay? And then finally, let me go ahead and switch colors one final time. We're trying to find the probability that they hire at most 2 or fewer women. So the probability that they actually hire 2 women is, again, the 20 factorial, because that's n factorial, 20 minus 2 factorial times 2 factorial. And then over here, the probability that I actually hired those 2 women, I've got 2 women, so those are those guys, and the 0.5 to the power of 18. These are the 18 other guys that they hired in that trial. And if you do that, all this factorial dividing by this stuff times all of these things here, what you're going to get is 1.812 times 10 to the minus 4, which again, if scientific notation really isn't your thing, that's 0.0001812. Have a decimal here, 1, 2, 3, 4. Scoot it 4 places to the left. That's all that means, okay? So the probability of hiring 2 or fewer women is nothing more than the probability of 0 women plus the probability that they actually hired 1 plus the probability that they actually hired 2. And when you actually add all of these things up, what you get, 0.002. That's the probability. So it makes sense. It's a very low probability, right? If someone's really hiring people with a 50-50, gender neutrality, right? It should be very low probability that they hire, only 2 people. It should be much more equitable, assuming everyone's equally qualified, right? So that's why the probability comes out so low, okay? Now, the other thing I'll say is that in these problems, we've calculated the probability distribution function. I've showed you how to calculate it. I've showed you how to set it up. I've showed you really what you're doing in your calculator is you're putting these factorials in. And most factorials, for the combination function, they have a button on there that you just press. You put 20 in there and you put 1 or 2 or whatever the bottom number is, and you stick it in there and you hit a button and out spits what the combination is. Now, a long time ago, before you could have the power of a computer in your hand, you couldn't do that. I mean, calculating all these factorials was labor intensive, especially if you had big numbers, okay? So in the back of all your statistics books, you're going to have a lot of tables. Usually you're going to have a lot of tables. Now, sometimes, for these kinds of problems, you may or may not have a great reason to use the table because the calculators are so powerful that you can actually crank through these pretty quick. But nevertheless, there are tables in the back of your book that you could use and you may be asked to use to get the same answers. It's really not doing anything different. It's just instead of punching numbers in your calculator and hitting a button, you go look at some tables that were made up. It's very similar to, if you open a trig book, if you're taking trigonometry or something, you look in the back, you'll probably see a bunch of tables to calculate logarithms or sine, cosine, and tangent, actual tables. Well, that's because there used to not be sine buttons on a calculator. So you couldn't do it until they put the tables in there. So there are tables here. I'm briefly going to give you a little rundown of how to use that. But really, for these types of problems, I don't think it's a big deal to actually just calculate it. So using the table is really just a backup method, or if your instructor tells you or asks you to do that, you really should know how to do it. Okay, so here's an example of a probability distribution table for a binomial probability distribution. So what you have here on the left are some columns n and x, and across the top you have the probability p. So really all you're going to do is find the intersection point of the numbers that you're dealing with in your particular problem. So let me give you a different problem. Let's say for whatever problem we were doing, n was 5, so the number of trials was 5, x was equal to 3, which would be the number of successes, and the probability p was equal to 0.3. So I'm not even giving you a word problem, I'm just saying n was 5, x was 3, and the probability of success was 0.3. So all you would do would be you would go down and you would go to the column that shows n, and you would go down to n is equal to 5. And then you see, notice right by n is equal to 5, there are different values for x. So right next to 5, you would find the value of x, which is 3, and you would find that. And then you would trace your finger across that row all the way to where the probability is 0.3, and you would look in that column and you would find out that the probability is 0.132. So it is pretty quick. If you know what n is, and you know what x is, and you know what p is, you can pretty quickly look in these tables and figure out what the answer is without doing all the factorials and calculating like that. And it's really useful if you're trying to solve a real problem and get a real back of the envelope, kind of answer without a lot of calculations. Okay. Now, this is the type of one of the types of tables that'll be presented to you that you'll need to use. They're very easy to use if you're just trying to find the probability of a specific n and x and a certain probability there. You would just go in there and you'd find the number and you'd write it down, and that would be your answer. That's one type of table. Now there is another type of table that is in fairly widespread use, and they don't. In the second type of table, they don't actually give you the value of the binomial distribution function at those parameters. They're actually putting the numbers for what are called cumulative probabilities. So what I'm trying to say here is there are some tables that are constructed a little different, and you have to know how to use them. Some tables, instead of giving you the actual binomial probability at that point, they give you the probability, like let's say you were looking up x is equal to 3, okay? N is 5, x is equal to 3. It wouldn't give you the probability 0.132 there. It would actually give you the probability that x is equal to 0, plus the probability that x is equal to 1, plus the probability that x is equal to 2. It's giving you the sum of all the probabilities of x equal to and lower than the one you're looking up. And you really just have to look at your table and figure out how it's constructed. And it's still really easy to use the table, but you really have to know what you're doing and know what kind of table you have. So let's go through a quick example to show you that. Let's look at this. Let's say that the probability is 0.2 that any given person dislikes a certain brand of potato chips, what is the probability that 5 of 18 people dislike it? Okay, so let's just run through what we know here. We know that there's 18 people that we're sampling, so n is equal to 18. We know that the probability that someone dislikes it in general is 0.2. Okay, and so we know that we're trying to find the probability of 5 of 18 people dislike it, so we know that x is equal to 5. Now, if your table was constructed like the one before, you would just look up these values and you would get the probability that, the probability that 5 people dislike the chip, and that would be what you did. But if the table is cumulative, which you'll just have to figure out for yourself with your particular book, then what you're going to have to do is you're going to have to do a little bit of subtraction, okay? What you're going to do in that case, if n was equal to 18, okay, and the probability of success was 0.20, which is what we're saying for this problem, all right, and x is equal to 5, that's 5 of 18 people dislike the chips, and those are my parameters. Instead of just looking up the value that corresponds to those two things, you're going to have to do some subtraction, okay? What you're wanting to find is the binomial probability that x is equal to 5, 18 is equal to n, I'm just writing down the numbers here, and 0.20, this is equal to p, okay? But in order to actually get the number you're trying to find, what you're going to actually have to look up in the table, let me just write it down and I'll show you. Okay, if the table is cumulative, then that means that every single entry in there is not just a value at a point, it's the sum of that value plus all of the probabilities of x underneath it. So to calculate at x is equal to 5, you'll have to take the value at 5 and subtract the value at x is equal to 4. Okay, this is x is equal to 5 and x is equal to 4. Because if you think about it, if this number includes everything below it, okay, if this number, whatever it is, includes x is equal to 5 all the way down to 0, right, then if x is equal to 4 covers all of this stuff, then by subtracting the 2, I'm actually only finding the value that I particularly care about, because everything in the table, in some of these tables, is actually a sum instead of just being a simple value. So you would look up this value, and then you would subtract the value right underneath it. The difference between them is going to give you what you want, which is the probability at that point. The reason they're done like that is actually because it makes some of the problems simpler if the table's actually constructed that way. So if you look in the table, okay, if you go to the table, if you see a table constructed like this, you'll go over to n is equal to 18, and then you'll go follow your finger down x is equal to 5, and you would go across the row over to the probability of 0.2 for this problem, and you would get 0.8671, okay, 0.8671, and then you would subtract it from it right above where you see x is equal to 4. So x is equal to 5 is this, and x is equal to 4 is equal to that, and what you're going to actually do is subtract those two values, okay, because it's a cumulative thing. So what you're going to find is 0.8671 minus 0.7164, and the difference between them is 0.1507. This is the number that you could find by looking in the other table, if you had a table big enough, if the table was constructed just to give you the values at these particular points, and then you could just do it that way. But some of the tables and some of the books are actually constructed in this cumulative fashion where every entry is actually the sum of all of the values of x, equal to and below it. So in order to get anything, you have to do some subtraction. Now let me give you a quick example of why a table constructed like this is actually going to make it easier, okay? Let's say that the probability is 0.05 that a pillar will fail, okay? Among 16 pillars, what is the probability that at most 2 will fail? At most, 2 will fail. So I know that I have 16 columns, and I know the probability that each one will fail. I want to know what's the probability that at most 2 will fail. So just like with anything else, you have to translate what does at most mean. It means I want the probability that 0 of these columns fail, plus the probability that 1 of these columns fail, plus the probability that 2 of these columns fail. Okay? So the probability that 0 of them fail, the probability that 1 of them fail, and the probability that 2 of them fail. So that's what it means when it says at most 2 of them will actually fail. So if you were using the other kind of table, you'd find this probability, then this probability, and this probability, and you would add them all together. But since some of these tables are constructed in this fashion where they're actually a cumulative table, you could do it really easy if you just go, in there and notice that in this case, n is equal to 16, x is equal to 2 because that's what I'm saying. At most 2 can fail, right? And the probability is 0.05. So if we go on into the table and look at what entry we get at that point, what we'll do is we'll go down to n is equal to 16, okay, and then we find x is equal to 2 and slide over to the probability 0.05, and we find the probability is 0.9571. Now, because this table is cumulative, what it means is that every single entry in this table contains all of the entries above it. So this number contains the probability of 2 plus the probability that 1 fails plus the probability that 0 of them fail. So this entry actually gives us exactly what we're looking for. Because it is a cumulative table, it already contains the probability of all of the other ones failing beneath it. So you don't actually have to do any addition or anything. You just read it right off the table, 0.9571. And so really you're going to be using the type of table pretty often if you have those kinds of problems where what's the probability of at least this happening? What's the probability at most this happens? It's really good when you're trying to find the probability of a whole bunch of events maybe added together. If you were using the first kind of table, you'd have to find each number individually and add them up. But if you're using one of these cumulative tables, it's real easy to read these values off because every value you read is going to be the sum of all the binomial probabilities underneath it. And if you want to find a specific value, you'll just have to subtract some adjacent values and do it that way. So in this section of the class, we've tackled a really important topic of the binomial probability distribution. And we've done it through examples, and we've done it through working step by step. So I really want you, when you're working these problems, to take it back home to our first example with the number of questions on the test and the number of right answers and wrong answers, and identify what the number of trials n is and how many successes you have and what the probability p and q is. And you can easily calculate these things with the modern handheld calculators. You can also use the tables as a tool as well. So you just need to be careful what kind of table you're using. Is it a cumulative table or not? It should tell you right at the top what type of table it is.